Again, just three last experiments to finish off electricity for us at the moment. The first is a thermistor, which is a temperature dependent resistor. They come in various shapes and sizes, and they are used in things like cookers and fridge freezers, air conditioning, central heating systems, to keep the temperature at a constant level, whatever we set it to be, and to monitor it as we go. So if we look at our thermistor at the moment, it's got a fairly high resistance, and the current that's flowing is 0.04 amps for about 16 volts. But what's important is not so much the value that it has at room temperature as what happens to the value of current that can flow, or the resistance to that current, as we change the temperature. So first of all, let's warm it up. If we place it in some boiling water, and of course if you're doing this experiment be careful, we find that the current has gone up by a factor of 3. It's now 0.12 amps, current going up really quite quickly, still rising as the thermistor reaches the same temperature as the boiling water, 0.15 amps. So the resistance has dropped significantly. The current is now over 3 times higher than it was at room temperature. So the resistance must have gone down by the same amount. Similarly, we take our thermistor carefully out of the boiling hot water. We can also cool it down, so I have some iced water here. And again, we give it a little while to adjust to the new temperature, to reach equilibrium with that new temperature, and while we do, we see the current dropping. So it's going from 0.15 down to 0.04, which was the room temperature value, and it should, if we give it a little while longer, go even further down. 0.03. See if we can get it to go to 0.02 as it cools down. Of course, it will be slightly warmer than the ice for quite some time, and in fact even when it's been in there for quite some time, the electrical current flowing through the thermistor will warm it slightly. So it's not going to go down to a zero current, but it's certainly dropped in current, which means the resistance has risen. So that's a thermistor. The warmer it is, the lower the resistance. It's a little bit like getting out of bed in the morning. If it's a cold morning, the resistance to getting out of that nice warm bed is quite high. If it's a warm morning, particularly in the summer, particularly if it's not a super all day, you might well find that your resistance is less. And that brings us nicely on to my next variable resistor, which is a thermistor. It's a light dependent resistor that behaves very similarly to the thermistor, but as the name suggests, it responds not to heat but to light. So we give ourselves quite high voltage. We find that the current is really quite small. But that's because the room is quite dark. If, however, I use a separate bulb on a different power supply to gradually increase the light level, we should find that the resistance of that light dependent resistor decreases and that the current rises. So there we've got a reasonably bright bulb, and the current is now 3 or 4 times higher than it was, so the resistance has dropped by the corresponding amount. We increase the bulb's brightness, the current increases, so the resistance is getting less, and again it's like getting out of bed in the morning. If it's dark, just as if it's cold, the resistance is going to be higher than if it's a nice bright morning. So a light dependent resistor you would find in a light that comes on when it starts to get dark, like some street lights, or in the sensor that tells your camera to set off the flash when it's too dim. Again, a very useful device, and its resistance depends on the level of light. Finally, we have just a piece of metal wire, which is all a resistor is. And I just wanted to finish off with this one because we've talked about resistance. We've talked about how some devices can vary the resistance. One of the common devices that we have around the house is something that can change the output. So the volume control on any kind of sound system or TV, the brightness level on a screen, or the dimmer switch on lights, and so on. It all follows the same basic piece of physics, and that's demonstrated with a single piece of metal wire. Now, resistance is caused by the electrons trying to get through and having collisions along the way as they travel through, in this case, a piece of metal wire. And we know that certain materials, metals, have a lower resistance than non-metals. So we call metals conductors and we call non-metals insulators for the most part. What we have here is a piece of metal, and it's quite thin, so the resistance will be quite high. But if I put a couple of volts through, I can get the bulb to light up. So I can put enough electricity through and I can make my bulb come on. If I were to use a thicker wire, the resistance would be lower. It would be easier for the electrons to travel, so the bulb would appear brighter. I happen to have a thicker piece of wire here, so there we are, brighter bulb. But the other thing that affects the brightness of the bulb and the resistance of the wire is how long the wire is. It's not because it takes the electrons longer to get through, it's simply that they're more likely to have collisions the further they have to travel. And this is how dimmer switches and volume controls normally work. They may be button based, they may be dial based, but basically what you do with them is you change the amount of metal that your electricity has to travel through. And as I make this wire shorter and shorter, we find that the bulb gets brighter and brighter. That's because the resistance of the wire is decreasing. So, longer wire, higher resistance. Thicker wire, lower resistance. If the wire gets hot, particles will move around more, and unless it's a thermistor, the resistance will increase again as well. And there you have it, resistance.